Thanks everyone for joining us today. This is our 6th Graph Guru webinar. We're super excited that you're here with us and learning about the most recent graph solutions with TigerGraph. Today's presentation is Birds of a Feather Community Detection with a Native Parallel Graph Database. My name is Emma Liu. I'm helping to moderate the webinar today. So a couple of housekeeping items before we get started. First of all of you guys are muted by default, but you can talk to us via chat in Zoom. If you have questions, you can submit through the chat and Q&A box, and we'll address them at the end of the webinar. And the session is being recorded. So after the webinar, we'll provide a link to the recorded presentation, and we'll send it through to your email. Please note, you should keep to update to the latest version of Zoom to avoid bugs. Some of our previous attendees had issues keeping the connection with their older version of Zoom. Lastly, I want to mention that with our most recent TigerGraph 2.2 release, we have a new Docker download and VirtualBox version for our Developer Edition so that you can install TigerGraph and learn about TigerGraph on your laptop. This is a beta release for the Docker and VirtualBox versions, and we welcome your feedback. All right, without further ado, let me introduce our speakers today. First of all, let me reintroduce myself. My name is Emma Liu. I'm a product manager at TigerGraph. I previously worked at Oracle as a software engineer and at MarkLogic as a product manager. My focus area is in cloud, containers, enterprise infrastructure, monitoring management, and ecosystem connectors. And our main speaker today is Dr. Victor Lee. Victor is our Director of Product Management at TigerGraph. As you can see, he has extensive background in computer science and technology industry. Victor also has a PhD in graph data mining. Joining Dr. Lee as the co-presenter is Huiting Su. She is a software engineer from our solution engineering team. Huiting has a master in industrial engineering from Purdue. She has a focus on graph algorithm, big data analytics, and machine learning. Huiting has helped many of our customers to build solutions using our GSQL language. She's our resident GSQL expert. In today's presentation, Huiting will show us a real-world demo around community detection using TigerGraph. All right, now I'm going to hand it over to Victor.
Thank you very much for that great introduction, Emma. And Emma is on the product management team with me, so we work together closely, and it's great to bring this topic to you and the audience together today. So today's Graph Guru's topic is part 2 in our series on graph algorithms. Last time we introduced PageRank. There are many different types of graph algorithms. So when we say a graph algorithm, what are we talking about? Well, they are algorithms that look at graph structure and graph properties in general and tell you something useful about that graph. They are application independent. They are like a toolbox, a set of basic functions, basic tools that you can use to develop your applications. And when I say basic, maybe I should say fundamental, because some of them are actually fairly sophisticated, fairly easy to explain, but to actually compute them takes quite a bit of work. And so they fall into different categories, such as here we're sort of looking at more the end use, link analysis, understanding your neighbors. Now that's the fundamental thing that graphs do, connecting to one another. But then you can start to look at what types of connections, how many connections, the hierarchy of connections, and trying to predict missing connections. Graph matching is looking at two different structures and seeing if they're identical. This also falls into the same general category as trying to find a pattern, providing a small little pattern and seeing if you find the same pattern within the larger graph. Frequent subgraph discovery. Here, you don't give any input. you just say, tell me what is occurring commonly. You're trying to find the trends from a network perspective, and so in that little example there, you see a blue, green, and light orange triangle pattern that occurs twice. And lastly, we get to the topic we're going to cover today, community detection. What are the natural groupings of communities within a graph? And then we'll have to look at what do we mean by a community and what do we mean by natural. So communities can be natural phenomena. You think about wildlife populations, you think about the way people tend to congregate. They even occur at the molecular level. Bioinformatics is one of the areas that actually really pushed graph analytics a decade ago. Here is an example on the left of a protein interaction network for the different proteins involved with schizophrenia. So you see little clusters there hubbed around little hub nodes. So you see the interactions are not random, they tend to occur in clusters. And on the right, this is a graph of DBpedia, which is a processed version of Wikipedia, where it's sort of structured the information a little bit better to say what pages link to what other pages and what basic topics do they cover. So here, somebody analyzed the entire graph of DBpedia and performed cluster analysis or community detection, so you can see natural groupings probably by topic. And I say that's natural because even though DBpedia is a man-made construct, there's no central authority. Everybody is creating their own independent page and deciding what to link to. Nobody is telling them, you have to link to that, you have to link to that. So the communities are a natural outgrowth of thousands and millions of individual decisions. So that's what I mean by organic or natural. Or you could have a community that is completely engineered from the top down, such as congressional committees and subcommittees. So this came from a research paper that was done about 10 years ago. So here's an interesting application that we've come across with some of our customers and people looking at using TigerGraph. And this was a use case from a large pharmaceutical. They wanted to look at the data of healthcare providers or prescribers, and in a particular region, so not looking at the whole world, but in a particular region and for a particular group of codes for a condition, such as diabetes. So diabetes might have several related healthcare codes. So they want to find what are the natural groupings of not which providers are working together in that sense. That's what we mean by a community. So first, who are the most influential ones? And then around these hubs of influence, who are they working with? Like, who do they influence? And then once we have these communities, to then assess the relative size and impact of the communities. So this can be really important. In this area, first, it helps to see what is the reality. How do things actually work in the real world? I'm a healthcare provider, or I'm an insurer, or I am an NGO who is trying to provide, or a government or NGO organization that is trying to see what we can do to deliver healthcare better. First, you want to understand what are the actual dynamics. Are there influential persons? Are there communities? And then where are they? How do they form? What affects them? If I know them, then what can I do? If I want to have impact, now I can think about what is the potential community I would be impacting. So it's very useful, and you can see how this could translate to lots of other applications, not just healthcare. So for this particular problem, again, so doing a little bit deeper dive, this requires analyzing the entire graph. And so you need a fair amount of computational power to do this. So the first thing is, when we had our raw data, or this provider did, they didn't have direct links from provider to provider. What they had were links from a provider to a patient or a provider to a healthcare claim, an insurance claim. There were no direct links doctor to doctor, but we inferred them. We analyzed the data and we said, okay, this doctor first provided care to this patient and for this claim, and then a small time later, Dr. 2 provided care. So we then inferred, okay, draw an edge from Dr. 1 to Dr. 2 because something that occurred in that case made a time sequence of care from Dr. 1 to Dr. 2. So we created that edge. So now you have a network of doctor to doctor or provider to provider edges, and we can perform PageRank on this to see who are the most influential doctors, who are sort of causing the most outcome. So again, for an example, let's say we're looking at diabetes, we're looking in the South San Jose healthcare market, and we identify the hub as a Dr. Thomas there in the center. I apologize if my voice is a little raspy. I'm getting over a cold. I'm hopeful that I will not start coughing. If I suddenly cough or turn off the sound briefly, you'll know why. Next, the next stage is we want to find those communities. So we can run a community detection algorithm, and that's what we're going to do today. So this is basically seeing who is Dr. Thomas potentially impacting. And again, so this blue oval represents his community. And lastly, once you know that community, using the other data you already know, you can start to consider how much impact does that represent? How big is the community? How many dollars are associated with it? How much resources? So not just the items, not just the fact that it is a person, a claim, but starting to look at the properties of those persons and those claims. So once you know the communities, there's a lot you can follow on analysis you can do. And again, some of the other use cases for business, who is conducting commerce with whom, or who has some ownership in whom, who has some deal with whom. So that could define a community. Yeah, who's trading? In government, trying to find the natural groupings of persons or their needs helps you to understand, could you deliver services more efficiently? Where are the natural boundaries? How to work with that. And in criminal investigation, big thing, trying to find collusion or conspiracy, a fraud ring, people that are connected who, if one person is doing something bad and everybody else around them is doing something bad, then there's a good chance that that other person is doing something bad. So humans have sort of an intuitive sense of what is a community, but it actually depends on the situation. And if we're going to do computational work, we're going to have to come up with a more formal definition. So here are 4 possible definitions. If we have a community C, which is a collection of vertices, excuse me, I think I need to clear my throat. Okay, let's try again. So if you have a community C, one possible definition is that everybody is connected directly to everybody else. Very strong definition. A slightly weaker definition, there's a path from everybody in C to everybody else. So you don't have to be directly connected, just connected. Third, well, you're connected to people, but in your community, but chances are you're also connected to people outside your community. It doesn't mean you completely ignore people outside your community. It's just that you have fewer connections. So now we look for the majority of your connections are within your community. And lastly, we take a variation of that and we look at, well, if edges were distributed randomly And so you had sort of uniform density. A community is a variation. It's taking away from that average density and redirecting it towards within your group. So the density of connections within your group is just greater than it would be if connections were random. So let's look at each of these. So first, if everyone is connected to everyone, you can see on the right, this is a very formal definition. It makes these beautiful geometric shapes. This type of subgraph is called a complete graph. And the collection of vertices that are members of a complete graph are called a clique. This is probably too strict for most real-world cases. It's used sometimes, but not that often. But mathematicians love it. It's actually also very computationally intensive to compute. So, number two, we're going to relax it a bit. There is a path to every member. So you can see on the right these three, what we call components. So a component or a connected component is the collection of vertices and their connecting edges that can reach each other through some path. And there are two variations. Weakly connected uses undirected edges, and strongly connected uses directed edges. So you see the one in the upper corner has little arrows, so that represents a strongly connected component, because you could see, you just go around the circle, and no matter where you're trying to go, you will eventually reach every other vertex. If we were to flip the direction of one of these, then you would see that suddenly it would not be strongly connected, because if this top one now we're going right to left, then if you start in this one, you only have in arrows, you don't have any out arrows, you can't go anywhere from there, so it's obviously not connected to the others. So two definitions, strongly you can see is a stricter definition. So this is useful sometimes, and it depends. It tends to be useful when there's a very big graph, different communities, the density is sometimes low. So it has to be low enough that sometimes you will see complete separations like this. Now we get into the messier case of where, yeah, everything really is just one component, but sometimes there's a higher density of edges, and that's what we're thinking of for a component. So you can connect to people outside your component. So if you look at this one up in the number 7 blue, so the top, the leftmost number 7, you can see that there are 4 edges within its community, but there's only one edge going outside its community. So that's why it belongs there. If we were to shift it over to the number 10 group, then there would only be one connection that justifies why it belongs in 10, but 4 connections going out, that just seems wrong. So clearly 7 belongs with these others, that number 7. And sometimes you get into the messy case of where there's a tie, and then you just flip a coin, basically. And you also can wonder, like, what if I keep cutting down? If I were to try to partition one of these, would it make it better? Or if I try to merge them, would it make it better? So that goes to the question of parsimony. This is usually how we kind of break those ties. The simplest answer is best. Also, it's kind of a restating of Occam's razor. It's using Occam's razor in an applied sense to make a choice. So if you have a choice of, should I use 2 communities or 3 communities, and both of them explain the data equally well, that is, it would sort of, for example, using the previous one, the number of joins within the community versus the number of connections outside, it's about the same, whether I use 2 communities or 3 communities. Then the parsimony principle would say, pick the smaller number of communities. Similarly, or in another case, if you have your choice between 3 communities will give you a cleaner explanation versus 2 communities, then go with the 3. You're looking for what seems to give you the the simplest and best explanation of the overall result. So that's a classic problem in optimization. So if you think again about the 3 algorithms we've looked at so far, this is a strict definition. There are really no choices to be made. This is also a strict definition. Number 3, now we're getting into judgments of what is best. And that's where you have to have some sort of rule in your algorithm, which is best. That rule may or may not fit your application. And that's why having something like the GSQL graph algorithm library, where you can go and modify it, makes a lot of sense, because I've got here a standard algorithm. It's going to make decisions a certain way. You might want to modify how it makes those decisions. That's fine. With GSQL, you can go in there and modify the code. And lastly, number 4. This says, again, where the number of in-group connections tends to be more than the out-group. And this is using a particular measure called modularity. Modularity is the fraction of the edges that fall within the group minus the expected fraction if edges were distributed at random. So expected edges, let's say you have 1,000 vertices and 2,000 edges. So the expected number is 2. It's the average, right? 2,000 edges, 1,000 vertices. The typical vertex, the average vertex, is going to have 2 connections. So that would be the answer here. And then modularity says, do you have more than 2 within your group? That confirms modularity. And so the algorithm tries to find the partitioning. It keeps rearranging the groupings until it finds the grouping that gives the highest modularity score. So there's actually a name for the 4 different cases I've discussed. Again, the first one we called complete graph. So that an algorithm which finds that for you would be called a complete graph discovery algorithm. The second case is called connected components. The third case, there's actually maybe a couple different ways you could do it, but the most common method is called label propagation. And the fourth one is called modularity optimization, and probably the best method to use it these days is the Louvain method, named after the University of Louvain in France, because it's just, they found the fastest way to compute it. So each of these algorithms, as we've seen, gives you a different result, and they also may take more or less time to compute when the graph is very big. So you may, until you become more familiar with them, you may just want to try all of them. And even when you have, you know what you're doing, there are going to be cases when you're not sure whether 3 or 4 is going to be better. So you could try both of them and see which one seems to explain your data the best. So again, TigerGraph recently released an algorithm, a collection of algorithms on GitHub. So the 3 that we're going to go over today are out there. And each one of those, they typically come in 3 variations. One that produces, each one is a GSQL query. I want to reiterate that. Our algorithms, they're not they're not like hard-coded functions. We have written GSQL queries to implement the algorithms using parallel processing. But they're quite readable, and from reading them, you can sort of see how things are done, and as I said, modify them as you wish. So a GSQL query by default produces JSON output, so that's one variation. Another variation is to output your data to a CSV file. And the third variation is to store the results back into the graph in a persistent way as a vertex attribute value. So that requires that attribute exists. So this one is actually modifying the graph. The other 2 are just giving you output data. So I'm going to look at sort of the concept of 2 of these algorithms and then go over the GSQL code with you. And then that will wrap up my part of the presentation. And then I'm going to turn it over to Huiting to do a demonstration of one of these algorithms with some of that healthcare data we referred to earlier. So the first algorithm I'm going to go over is the connected component algorithm. So here's a simple pseudocode description, and you can see it really isn't that complicated. So you label every vertex with a unique community ID. That is, this vertex is labeled as 1, the next one is 2, the next one is 3, etc. And that represents their community ID. So initially, every vertex constitutes its own community. Every vertex is an island. And what the algorithm is going to try to do is to join them into, so they decide, oh, these two actually belong to the same community. So we iterate through all the edges. So for each edge, you look at the IDs, the community IDs of the two endpoint vertices, and the target vertex will be updated to be the smaller of those two. So either it changes itself to have the ID of the source vertex, if the source vertex had a lower ID number, or it stays the same because it already had the lower ID number. Now you say, why am I changing only the target vertex? Don't I need to sort of change both of them? Well, the reason why is in GSQL, if you have undirected edges, it will actually treat it as two edges, one going in each direction. So I will end up working with both the target vertex and the source vertex because I will handle that edge twice. So that's one iteration. So every edge you look at, set the two endpoints to be the lower of the two IDs. So you could imagine that sort of typically on average, after one iteration, you've cut the number of different IDs in half. You now have half as many IDs, and everybody's in communities of 2. It's actually not going to be quite that simple, but you can imagine that is just to get an idea of what's happening. So the number of communities is going to keep going down, and then the number of members is going to keep going up. So you do that iteration once, and you keep repeating until basically there are no more changes. When you got no more changes, things have stabilized and you're done. This is how it looks in GSQL. So we define 3 accumulators at the top, and if you know a little GSQL, an accumulator is a temporary variable. The single ampersand means that there's a variable for every vertex. So every vertex has a CC ID, an old ID, and an active. You can imagine this is the community ID I was talking about. Old ID is the previous one from the previous iteration. And active is a Boolean flag to see whether it changed in that iteration or not. And the one thing also to note is that the CC ID, it's a min accum. And we'll see where that is used later. So the initialization step, we make the start set equal to all vertices of type node. So node is a vertex type here. And then we do a select statement, a select block from, all the start vertices, so every vertex of type node. And we're not looping. We're not doing any edges. We're not traversing any edges. We're just iterating over the vertices. And what we're doing is we're just initializing the values for CCID and old ID. And we're using a built-in function to get an internal ID. So this is not the ID that the user assigned. This is an internal integer code that GSQL uses. So we don't really care what the number is. We just want it to be unique. So every vertex is given a unique integer ID. That's the initialization. The next step, we do a while loop. So you can see, GSQL is very much like high-level programming at times. A while loop. We're doing edge iteration. So from start across all link type edges to any target. So see, the graph consists of node type vertices and link type edges. And this is where the accumulation comes in. Remember that CCID is a min accum. That means that when you try to accumulate the source vertex's CCID to the target vertex's CCID, what you're really doing is you're comparing the two and seeing which is the minimum and saving the minimum to the target. So that's exactly what we said in the previous page. We want the two endpoint vertices, target and source, to end up with the minimum of their two ID values. So that's what that statement does. As an update step, after you've done all that, then the follow-on step is to see, did we change the CCID? Compare current CCID with the old ID. If it has changed, then update old ID and set active to true. Otherwise, set active to false. That's the entire sequence of operations. This last step is saying having t at active ID equals true. That's saying in the output set, only include the vertices that changed. So if a vertex didn't change, don't include it in the output. So that way, that's how we're seeing whether we've reached stability. It's also optimizing the amount of work we do. We don't need to work with the ones that didn't change. It is possible they will pop up in a later iteration, but for the immediately next iteration, we don't have to deal with them. So that is that algorithm. And here is a result. So now the graph on the right actually represents a very famous data set. It looks very small to data scientists today, but back in the 70s, this was important. And it's still useful for little demo examples like this, where you want to get your head around the data. So Zachary's Karate Club represents a real karate club of 34 members, started out as one group, and then they had some falling out and they split into two groups. So you can kind of see that the upper half is one group and the lower half is another group. It's a little hard to tell from this picture where the cut line is. But it is one connected component. So every vertex there is blue. That's because they all belong to one group. So for this data set, this was not a useful algorithm. The algorithm in general is fine, but it just told us that everybody's connected. Nothing too special there. So let's try label propagation. Label propagation, if you remember, is trying to do majority voting. You belong to the community where most of your neighbors belong to. So we start off with the same initialization, everybody with a unique ID. The next step is you do a tally of which community does each of your neighbors belong to, and then you update your community to be the same as the most commonly seen among your neighbors. And again, if there are no changes, or if there's a maximum number of iterations, you stop. Because this algorithm does have a possibility of bouncing back and forth, and so you just have to make a decision to stop at some point. So it's a little bit longer, so I've split it up into two slides. So here we look at the accumulator declarations at the top. The first one, again, is one of those Boolean flags to tell us where anything has changed or not. The next two are the really important ones. The first one is a per vertex, and this is where we're doing that tally or their count of how many of your neighbors belong to each community. So it's a map. The key is the community ID, and the value is the number of times you see that community ID. The second one, called com sizes with 2 ampersands, this is a global accumulator. That means there's only one of these. And again, for each community, it counts the total number of vertices. So if you were to add all of these, you might say community 1 has 10 members, community 2 has 20 members. So the total is, what did I say, 10 plus 20, 30, which should be your whole graph. And then these are some more sort of local computational things we need. little variables. So we do similar initialization. This is the last detailed slide I have, and then I'm going to turn it over to Huiting. So again, we have a while loop. While something has changed and we haven't yet reached our limit for the number of iterations, traverse the linked edges, source to target, S to T, and for the target, add to its map. Look at one of your neighbors. So these are the edges going from source into target. So when I talk about neighbors, this time we're talking about your in neighbors. So a source belongs to a particular community, and the associated value is 1. That's a tally of 1. So in other words, if this is a new label you haven't seen before, then associate 1 with that. If you have seen it before, you don't need to add a new label to the map. You just increase the count by 1. So we're keeping a running total of how many times you see each of these labels. So this is the technique. This is something you may want to do a lot in GSQL, keeping when you're traversing, counting how many times you see something. This is how you do it with a map accumulator, and this is the map accum syntax for how to add 1 more to the count. Post accum. So after you've gone through all the edges, now do a secondary step. This is basically, I'm not going to go line by line. This is basically seeing which one of these labels occurred the most. Set that to be the max v, that would be the count max v, yeah. Which of those occurred the most, and record that value. So, and lastly, this is only find out, does that represent a change from last time? So maybe the label that occurred the most this time was the same as the label that occurred last time. Or maybe it's different, but it's not a higher count. There's no reason to change because it's not higher than before. So, because we only want to make changes if they make sense, because we want our algorithm to end eventually. So that's basically what that algorithm does, and this is what the result looks like. So here's one of the karate clubs. Here's, you see, this is, you may have reading it, but this is the original sort of president of the club. He had a falling out. 34 set up his own club. 33 was a close associate. 2, this is 1, 2, and 3. So these are sort of the key members in group 1, and 33 and 34 members in this other group. And then why are these people colored differently? It's because they have few connections to the greater group. They're not as tightly associated with the group. They're not associated with this group on the left either, but they're just not that tightly associated with the yellow people. And this person is blue because he has 1 connection to red and 1 connection to yellow, and it's a tie. It couldn't really have a reason for putting him more strongly in one group or the other. So that is my overview of the general idea. I have taken a lot of your time. I hope you can take a little breather now while Huiting is going to take over and do a demo for you, and then we would love to have your questions. Huiting?
Thank you, Victor. So I'm going to share my screen. Can you see my screen? So if you cannot see my screen, just send a chat message in the chat. So I will show you how to run the community detection algorithms in a real-world case. This is the same case as we used for the last graph guru on PageRank. So let's take a quick look at the schema. We have prescribers. They will submit claims for patients, and they have referral relations between prescribers. Here, you can notice that I added an attribute called community. This community attribute will store the result of our community detection algorithms. In our graph, we have 11,000 vertices in total, and there are more than 100 prescribers. Let's see, is there any problem in the chat?
Yeah,
Okay,
there seems to be some problem in the
then,
audio.
we added,
I
as
can see
before,
your
we added referral edges. We insert a referral edge if a patient see prescriber 1 and see prescriber 2 within 2 weeks. We can visualize those referral edges. So clearly, there are 2 different components. Some prescribers are connected to each other, but these 2 components are not connected with each other. Then we can try the connected component algorithm. So the result shows that for a community, for the first community, there are 92 prescribers. In the second community, there are only 13 prescribers. We can use this label to show different color. So we can add a rule that's saying that we want to show the we should want to show different color for different prescribers. So we can set the attribute name community equal to the first community label. Okay. And we can see that the first component is blue. And we can also do this for the second community. So we can clearly see the result of the connected components. It clustered the prescribers into 2 different communities. All the others are not connected, so they are in other different communities. Yeah. And let's see. So in this community, there are a lot of referrals between the prescribers. On the referral edge, we can see how many referrals they made between each other. So the Douglas Thomas have made 10 referrals with the Helen Sue. And here, he also had referrals with other prescribers. And there are 11 referrals between Helen Sue and Don Kirk. Then we can also try the label propagation, and it will give different result. The max iter here is the maximum iteration that will run in the algorithm. Let's take this large community. Let's change it here. And the second large community. Okay. Sorry. Let's do that again. Okay, this is fine. And the second one. Run this again. Okay. Then we can see that the previous cluster is still, this community is still clustered together because they have a lot of referral relation between each other. And it is a natural cluster that we want to show. And then in this big component, there are a lot of different communities actually, because they are not connected, so they are connected more sparse. And for this community, we can see that they have a lot of edges between each other. We also have a lot more communities here. For Loven, we also have a lot more different communities. But for the time limit, we just we will not show the demonstration for the Loven. Okay, so Victor and
Okay, thank you. So
right.
I think we're ready for your questions now. So I think I'm gonna let Emma.
Yeah, okay. So I've got a few questions on the Q&A and chat box. First of all, I want to rephrase one of the questions that Victor answered in the chat. So one of the attendees asked, is this algorithm to find the ID which has the smallest distance with others in its group? I think Victor clarified that he's asking about the distance. The first algorithm, which is the connected component, and Victor said the connected component algorithm is a black and white, do you have a connection or not algorithm. So there's no sense of most or greater. I just want to repeat for everyone who haven't seen the answer. The second question I got here is, how do we apply Bayesian knowledge? Example is, in medicine, cardiologists may often have patients with related illness like high blood pressure or a kidney problem that may speed clusters by likelihood. Victor, do you want to address that question?
Sure. So let me look at the question again. So it is talking about Bayesian likelihood, which is really one of the fundamental ideas in statistics and probability. So I think this is coming down. So there are a couple. There are clustering algorithms which are based on Bayesian methods. And there's also, so there are two things I could see that the question might relate to. So the probability could relate to likelihood that a relationship exists. So it could actually be in the data. In that case, we have weighted edges. So the weight of an edge represents the probability that there actually is a connection or not. And so then there are algorithms which look at the weight of the edges. The algorithms we presented assumed that an edge either completely exists or doesn't. So they were presented as completely certain facts. But there are different algorithms which look at weights. Now, I think what the questioner was actually asking is, can we apply Bayesian likelihood to making the decision about where to draw the partitioning lines? And you can, and there are other algorithms. We just didn't have time to present any of them today. As I said, we pretty much have taken up the full hour with the basics here. We don't have any of those Bayesian algorithms in our library yet, but we are planning to add 1 or 2 algorithms per month. So if there's a particular one you'd like to see, send us a message and we'll try to prioritize it.
All right, thank you, Victor. There's another question. How do you install these algorithms? Victor, do you want to address that?
Yeah, so if you follow the link to our graph algorithm library, I showed it on screen, but if I'm certain you may not have memorized it there. So if you just go to our documentation website or go to our developer portal, or just send us a support question, we'll be happy to point you to it. So all our graph algorithm libraries are on GitHub. Because these are just GSQL queries, they are not directly a part of the product itself. So once you have the TigerGraph platform installed, you can then take the algorithms, and then we have an install script. The reason why there's an install script, there are a couple things that you as the user may select for how you want to customize them. You know, the algorithm, which vertex types, which edge types do you want to look at? What's the name of your graph? As I said, we have these 3 variations depending on what type of output you want. We usually just produce all 3 for you. And some of the algorithms will work with relatively old versions of TigerGraph because they really don't call upon any special features. The one new special feature, actually the ones I showed you today, where they have the getVid function, that function was added in 2.1.8. So you need at least 2.1.8 or newer to use these algorithms. So basically, just download the code. There's a README file. There's an install script which you run, and bam, they're in. Okay?
All right, I got the next question. This is a really cool demo. Is there a limit to the number of nodes we can process for community detection with TigerGraph? Huiting, do you want to address that?
So a limit for the number of vertices that we can process. TigerGraph is a parallel scalable database. So by the visualization, we are limited to 5,000 vertices because more vertices does not make sense to the users. But if users want us to show more vertices, we have a partner called Graphistry. Then they can do really cool visualization for you.
All right, thank you, Huiting. Okay, I got this next question. How do I apply these algorithms to my social media data? Victor, would you like to address that?
Okay, so great. As we explained earlier in the presentation, there are a lot of different ways. Once you become familiar with these algorithms, and these are like tools in a toolbox, then there are many different ways you can apply them. So it kind of depends on what sort of social media data you have and what the aims of your organization are. Are you trying to do advertising? Are you trying to, detect trolls or fraud? Are you trying to, do trying to see what are your most popular products among different groups? Really, what are you trying to do? So I would say one of the first questions you have to start with are, well, what are my node types and what are my connection types? Graph algorithms tend to assume a homogeneous typing system. That is, they think about only one type of vertex and one type of edge. So even if you say you want to consider 2 types of edges, say in a social network, A likes B, so a like relationship, or A recommended B, so a recommended edge, so those are 2 different types of edges. The algorithms tend to only think about one, so it's going to lump them together. You also think about what type of nodes do you have. Does does the property that you're interested in, does it exist currently as a node? One of the great things about graph databases, and TigerGraph in particular, is that it's really easy to change the structure of your data. Maybe there is an attribute that you have that you actually want to think about trying to cluster, and so you actually want to promote that attribute to its own type of node. You can do that. Or suppose, like in the example we actually showed, where we were finding communities of healthcare providers. If you remember, we did not have edges from doctor to doctor. We looked at our raw data, we saw a time sequence of care, and we created edges. So, if trying to apply it to social media, any application, what is it that you want to accomplish? What is the structure of your data? Possibly, massage your data until it fits one of these algorithms. And if you have a more particular question, we'd be happy to have like a one-on-one discussion with you.
All right. I have another question. I think here's this a participant is asking. You're talking about there's 3 outputs that the algorithm can export. The third one requires the attributes to exist to export back to the database. Does it throw a warning if those attributes does not exist?
Actually, the query will not compile, so there will be a warning. It actually during the install script, it will ask you which attribute do you want to store back to, and so if you don't give a valid answer, it won't complete the installation.
All right, I think we answered all of the questions, and so we have a developer portal, and if you have questions and you want to try out all the scripts, you can find information from the developer portal and also our GitHub link. It's tigergraph.com/developers. And we also have upcoming Graph Guru more episodes in December. So you will be able to find all those information from our developer portal as well. Yeah. Thank you, everyone, for joining our webinar. This is information for the webinar for the December. The next webinar is connecting the dots in real time, deep link analysis with a native parallel graph database to uncover hidden relationships. Thank you again for everyone to join us. We're happy to see you again for our next webinar. All right, bye.